All right, evening, ladies and gentlemen. This is our introduction to Chapter 5. Here's kind of a little overview for you, what's coming up, and where things are going to be situated. Obviously, there's no dates with this, but we basically have until the end of the quarter, which is December 17th, to finish this stuff up. So I think we can do this pretty good. All right, so we are starting our study of the integral, the definite integral basically, and some antiderivatives. And you'll notice down here in 5.4, one of our big theorems called the fundamental theorem of calculus and the trapezoidal rule. All right, so basically we're finding area. And area is not a hard problem at all. We just got to remember how to do it. All right, so let's move forward to 5.1. We're looking at estimating with finite sums, and some of you might remember that RAM right down here from last year. Those of you that had me last year in pre-calculus might remember the RAM, and those of you in the trig algebra 3, this is pretty new to you. So let's go ahead and see what this is going to look like here. So I'm going to start off with basically the same problem I started off with last year when we discussed this, and the basic problem is the one on the left. So you traveled, or your distance traveled by a 75-mile-an-hour train for 2 hours is 150 miles. So you notice here we traveled for 2 hours from 7 to 9. Didn't matter where we chose the h value or the time value. And we could travel at a constant 75 miles an hour, so we would have a constant speed. Well, it turns out that just this 2 times 75, that 150 miles, is this area underneath the curve. And this little area here is the 150. It's 2 units this way, 150 units up. Or sorry, 75 units up. And then what the question is, well, what if you weren't traveling at a constant speed? Let's say it was a variable speed, and you knew the time period that you traveled between. So if your velocity varies over time, the question that came about was, the first question's really easy. Well, yeah, obviously this area is correct, and it is my distance traveled. So then the question became, well, does this shaded area give you distance traveled as well? Well, if you might remember from last year or from anywhere else, it turns out that it does. And what it requires is to find area. Well, we can't, and we're doing it by hand at first, right? So we don't know the function, but it required us to find some area. And one of the easiest area formulas is a rectangle. So what we're going to do is we're going to break it into partitions. So you notice my little thing here. We broke these into little intervals, right, of some unit. We usually use an x sub I. We're not going to really get into that definition in here. We're just going to look at this, looking at a whole bunch of different rectangles. And if you think about, we could actually find the rectangle's area by figuring out this height and using these rectangles to find the area. Well, actually approximate the area. We're not finding the area, we're approximating the area, which is where we get the RAM, so the rectangular approximation methods. All right, so in pre-calculus, we discussed the top two here, the left-right approximation, the left approximation method and the right approximation method, or the left rectangular, the right rectangular. And what we did was we used the left side of our interval to find the height. Then we used the right side of our interval to find the height. And then for our class last year, we found the average of the two, which gave the middle. Well, it turns out we actually have a midpoint rectangular approximation method, the MRAM, and this uses the midpoint of our interval to find the height of the rectangle. And what we're going to do for the most part today is we're going to look at MRAM, even though I will discuss LRAM and RRAM. I might even do the first problem with all three. And what I did on our calculators, or my classroom set of calculators, I entered a program I found online that will do LRAM, RRAM, and MRAM up to 999 intervals. It won't do 1,000 for some reason, but it'll do 999 intervals. And it's going to be helpful for us because there's a couple problems where we need to use the calculator. So I entered the program onto my calculators, the 84 plus CEs. And any of you that have that, I can download the program to you onto your calculator. It takes like 5 seconds. All right, so we'll do that Friday when you guys come in and see me. So here's our first example, an example we actually used last year. And we're going to look at this and go, okay, so I have the function x squared on the interval from 0 to 3. Oops, too far up. And here we go. Where am I at here? I'm not going to do that. Okay. Looking at the function from 0 to 3 for the function x squared. Let's use a different color here. Well, from 0 to 3, basically my function looks like this. I hope you knew that already. This is the quadratic in the first quadrant from 0 to 3. And what I want to do is let's just stay with the 3 intervals here. We could break it down smaller because the smaller intervals that you get, the more accurate your answer is going to be. And let's go ahead and just do LRAM first. So let's use the left side of my box, or left side of my intervals. So my interval, breaking it into 3 intervals here, I have a single interval from 0 to 1, one interval from 1 to 2, and an interval from 2 to 3. So these are going to create my rectangles. Now, from the left side, which is x equals 0 here, I have to go up to the curve. Well, that's just a height of 0. So we have a box here that has, my first interval has a width. So remember area, by the way, it's length times width. Actually, in our case, it's height times width because we're looking at height, but it doesn't really matter, right? So we're looking at a height of 0 and a width of 1. And you'll notice that the widths are always the same here. And the next one, if we go up to the next interval here, from 1 to 2, I'm going to use the left side of my interval, which was 1. And if I plug in x equals 1 to the function, I get 1, which is my height, and 1, which is my width. And I'm going to go on and I'm going to do the last interval from 2 to 3. And you'll notice the width is still the same, only this time the height is, when x is 2, it comes up, touches the line. So plugging 2 into the function, we get 2 squared, which is 4. So my height is 4. And my width is 1. So we add this up. And for my LRAM, we get 0 plus 1 plus 4, which is 5. Now, you have to remember that this is not going to be a very good approximation because these are very big rectangles and there's lots of empty space. But if we do the RRAM, and you remember this was a under approximation for the LRAM in this particular case. If we did RRAM, this time we're going to go from the right-hand side of my interval. So up from 1, we're going to create a rectangle this direction. Sorry for the curved lines there. Then we're going to go up from 2, and we're going to go back to the left. Now we're going to go up from 3, and we're going to go back to the left. And you'll notice that this is an over approximation because there's more on the shouldn't be counted. So we're going to get a height of 1, then a width of 1, which we're always going to get, plus a height of 4 times a width of 1, plus a height of 9 and a width of 1. And we're going to get an approximation of 1 plus 4 plus 9, which is 14, I hope. And now the one that we haven't done before. So let's go ahead and go with MRAM. And we're going to use green in this case. And I need to get rid of some of my lines because I need to be able to see this here. Oh, dang it. Oh well. I'll redraw it. Okay, so, what color was that? Dark blue. Okay, so let's go ahead and draw this again. Basically, and it looks a little bit different, but it's okay. All right, so let's go. Oh, this thing's gonna be a pain to me today, isn't it? All right, so here we go again. And all right, so my MRAM is going to be from the midpoint of my first interval. From 0 to 1, my midpoint is half. So I'm going to create a box that has a height when x is a half. Then my next height is going to be here at 1.5, halfway between my intervals. And the next one here is going to be 2.5, halfway between my intervals. And you'll notice that this one's actually kind of a nice method because it gets a little bit of an over approximation and a little bit of an under approximation. It's kind of like an average, right? It's kind of like an average of R and L. All right, so let's look at what this is going to look like. Well, all of my heights are going to, or sorry, all of my widths are going to be 1. I just got to figure out what my heights are. I have to go to the left because I don't have room. So at 1/2, I'm going to square that, and I'm going to get 1/4. At 1 1/2, which is actually, what, 3 halves, so I get 9/4. And this over here is 5 halves, so I get 25/4. So I get 1 plus 9 plus 25, which is 35/4, which is approximately 8.75. And this should be a pretty closer approximation than both of these, and it is. But you notice if you take the average of these two numbers, 5 and 14, you get, what, 9.5, which is actually pretty close to this number. And the more intervals that we do, the closer that we get. So if I was to say, let's just go ahead and clear this if I did this really quick, and I said, all right, so here's your graph. And I go from 0 to 3. And I said do LRAM, RRAM, and MRAM. And you need to do this on 50 intervals. Well, you're not going to want to do that by hand. So that's why I went and found this program for you. I'll show you guys how to use it on Friday, because obviously you guys don't have it right now. But you need to plug in your equation into your y equals, which here, I'm doing this really quick just so I can show you what it's going to look like here. And program, RAM, number of intervals. The first thing it asks for is number of intervals, so I want to do 50. My left endpoint is 0, and my right endpoint is 3. And what's super nice is it's going to give you 3 answers. It's actually going to give you LRAM, and at LRAM it gives me 8.7318. RRAM it gives me as 9.2718. And MRAM it gives me of 8.9991. And the more intervals you use, the better approximation it's going to get. And let's see, if you were to actually do, if you knew how to do this later, actually in like a couple weeks we'll know how to do this. Actual answer is going to be, let's see, 3 to the third divided by 2. Oops, sorry, 3 to the third divided by 2, not divided by 2, divided by 3. Three to the third, man, gotta pay attention, is 9. The actual answer here is 9. The area under this curve from 0 to 3, that area actually totals to 9. It's kind of cool. It comes out as a really nice number. But that's why we choose this particular problem, because it does come out to a very nice number. All right, so you'll notice that these approximations are pretty close to 9, which is good because that's what we wanted it to be. All right, so again, I'll show you how to use that program tomorrow in class. It's not too bad at all. Let's go ahead and move a little bit forward here. This is where things start getting more and more challenging, and that's estimating the volume of a sphere. Now, I know we know the equation for a volume of a sphere, but what we want to figure out is using MRAM or RRAM or LRAM, anything of those. We usually use MRAM because it's a better approximation. How can I estimate the volume of a sphere with radius 4? Well, what we need to do is we need to know what an equation would look like on a Cartesian. So basically a sphere is a circle. So we could draw a circle with radius 4. And what we're going to be talking about later is rotating this around one of its axes. And if we rotate a circle, we get a sphere. That's where a sphere comes from. It's a rotation of a circle because it's a circle in every direction. So what we need to do is we need to figure out an equation for this. But we need to figure out an equation that's a little bit simple. And we only want to think about the top half of this circle. And I hope you guys can remember that you have x squared plus y squared equals 4 squared, so you get 16, which can help you figure out that we need an equation that says y equals the square root of 16 minus x squared. Okay. So looking at that, that will help us figure some stuff out. So we need to think about finding volumes. And this is going to get really tricky here because we are finding volumes of revolution. This is where it gets a little bit hard. All right, so we're going to think about, it's hard to draw this. I wish I would have taken the picture from the textbook. You guys have a picture in the textbook about this. We're going to do 8 subintervals. So basically we're going to use just whole numbers here. And here at 3, between 3 and 4, we're going to go up, and that's going to be the radius of the circle that I want to find the area of, or the volume of. So we're looking at disks now. So we're looking at a circle with a width, with a depth. And so and these are all cylinders, right? So if you look at the picture in the textbook, you get a whole bunch of cylinders. And each of these cylinders have a width of 1 and a radius of whatever that height is, going back to this equation. And for a cylinder, oops, that's not how you spell cylinder. For a cylinder, it's pi r squared h. Well, in this particular case, my h is all going to be 1 because that's going to be the height of my thing. So we're looking at a whole bunch of pi r squareds. And how many of them are we looking at? We're looking at 8 of them. And we need to know what r is. Well, r is defined by this equation because it's the distance from my axis up to my circle. So I'm looking at an equation that is actually pi times the square root of 16 minus x squared squared. So I can use my MRAM, to go, okay, well, all of my heights are 1, so here it's not going to be important to use my h, so I'm going to have pi times the sum of all of these things, all of these heights. So we're looking at 3.5, 2.5, 1.5, 0.5, negative 0.5, negative 1.5, negative 2.5, and negative 3.5. Those are all going to be the midpoints of my cylinders. I'm really bad at drawing, so I'm not even going to try. I'd suggest that you guys look in your textbook for the picture of this. This is going to be on page Where'd it go? Should have had it open already. This is going to be on page 267. So if you want to kind of see where this is going here, page 2, oops, black doesn't work right there. 267. You'll see these volumes of cylinders. So we're estimating the volume of a sphere using approximations of volumes of cylinders. And now we can do this by hand, so we would technically go, okay, so it's going to be 16 minus 3.5 squared plus, that's my first radius. Sorry, I put my squares in the wrong spot. 3.5 squared. Plus 16 minus, the next one is going to be 2.5 squared plus, now we just keep going like this. Notice here I'm using 3.5, 2.5, 1.5, 0.5, and we just keep going like this. And I'm going to kind of cheat a little bit here. I'm going to use my calculator to figure out what I get for 8 different slices. Okay, so if I use my program that I created, it gets a little bit ugly for this particular equation, but we get pi times the square root of 16 minus x squared into my calculator, and we quit this, so we go in here and we go like this, we go 8, and left endpoint is -4, right endpoint is +4. And for this, for MRAM, doing these calculations by hand, you should get this. You should get an MRAM of 270.177. And then the more intervals you do, you can do the same thing. You can do number of intervals. Let's say if you look down at the bottom of page 267, it's actually got some examples. And let's just say I did 10, left endpoint of -4, right endpoint of 4. Hey, I actually got exactly the same number that they got. So if I did 10 intervals, I get 269.42299. So this is the handiness of the calculator, obviously. You can plug these numbers, you can plug this equation into the calculator here and actually use the table values. Actually use your table on your calculator to get these numbers here, 16 minus 3.5 squared, 16 minus 2.5 squared, 16 minus 1.5 squared. And those numbers all the way down to this -3.5. All right, so when I ask you to do it by hand, you need to do it by hand just to get the process down. A lot of this stuff today is going to be from the calculator, so it'd be a good thing to have the program. I will try to install the program on one of the older calculators so I can give it to the other calculator people as well, the TI-84s, the older 84s, even the TI-84 colors and that sort of stuff. Okay. But again, this is going to be actually a pretty useful thing if you ever have to do it on an AP exam. I can't guarantee that it's ever going to be there, but maybe it will. Now, you got to remember today all we're doing is really estimating areas and volumes using basically areas and volumes again. All right? Oops. What happened here? Why'd that do that? Couple little things that you want to remember here. Sorry about that little pause there. Couple things you want to remember is if you have a velocity function, which they're going to give you quite often, I would think. When you're given a velocity equation, a velocity function, the area under velocity is distance. And what you want to think about is what's the derivative of distance? Well, the derivative of distance or position, the derivative of distance is velocity. The derivative of velocity is acceleration. So we can go the other direction now, and that's really what we want to do. Okay, There'll be going to probably be a problem on here somewhere that you want to look at a cardiac output. It's basically the amount of blood your body pumps out. And you can do the area under the curve, and then that's going to get you the area here. So what you want to do is to figure out cardiac output is going to be calculated by take the milligrams of the dye that's being used. So you actually have to read the word problem and divide by the area under the curve. And usually, or not usually, depends on the problem itself. Some problems you'll get it in seconds, and if you want to change it to minutes, you just multiply by 60. Right? That's the basics of today. I think that will get us through everything, but you never know, right? So I think I explained things, and you know how it goes. So here's the first lesson. I'll get you guys an assignment sheet tomorrow. If I don't remember, just remind me, and I will get it printed off for you guys. All right, thanks for listening. I will see you guys in the morning.